Hi, welcome to another video on GD32VF series microcontrollers. So this time we'll be looking into the coding and other stuff. As I have mentioned, the Segger Embedded Studio IDE is the platform that we'll be using for coding the GD32VF103 series. So this is the Segger Embedded Studio version 8.24. As you can see, during startup we will get a message like this, and it says about the license. It says a license for commercial use could not be found because I don't have one. I am using it for non-commercial and educational uses. So it also says please click accept to use software under the terms of Segger's friendly license for educational purposes, for teaching yourself, or as a part of university course, or for non-commercial projects. So that's the category I am, so I'm accepting it. So just after startup, there is a code template, as you can see here. So we won't be needing this one, so I'm closing this solution. So the very first thing that we will be needing before using the Segger Embedded Studio for GD32 coding is to download the stuff that we'll be needing for the GD32VF103 series. So let's go to the tools and then go to package manager, because by default Segger does not install the packages that we will be needing, because there are, as you can see, lot of packages from various ARM, Cortex and RISC-V vendors. We have Nordic, Novoton, Raspberry Pi, ST, Renesas, just a few to name. You can find it for yourself. There are a lot of MCU families. In fact, some MCU families have very different versions. Like in case of NXP, there are the LPC series microcontrollers. Then there are also the MIMX series, the MIK series, etc., etc. So there are a lot of options. So in our case, we will be needing the Giga device, and it also has support for almost all of its MCU families, but we are particularly interested in the VF series, which I have installed. If it's not installed, just click here and you will see options to install or not, remove it or reinstall. So since it's installed, I'm not going to do anything else. And the other things like the CMCs and other stuffs are just optional. You can customize your embedded studio as per your requirements or as per the families you will be using in future. So, and then there are some example codes, as you can see here. There are examples for all the families that I have here with me downloaded, but this is not something I will be showing you. I will be showing you how to do the coding. So first, let's see ready-made code that I've already created, and from that we will see how things are done. So let's open the solution. I'm showing you the very basic example, LED blinking, and after so many years of experience, I have found out the most interesting stuff when you start with a new microcontroller is obviously a LED blinking, because that gives you the motivation to drive forward. So I'm showing you this GPIO example. This is the basic example. As you have noticed, this board, the Cypet Longan board, has three LEDs. It's basically this one. This is the LED, and it's a RGB LED. It's a RGB LED, and the red LED is connected to PC13, the green one to PC1, PA1, and the blue one to PA2. So this is the LED, onboard LED. So this is a charm because most development boards come with single colored LED, but this one has the RGB LED. It's very nice to see such a thing. So before I proceed, I recommend that if you are using or if you are planning to use this board, the Cypet Longan, which is widely available, then I suggest that you also have this pin map downloaded, because that will be a real time saver. So moving on, as you can see, these are the pin and port definitions that I have defined, and this is the code. I believe that my regular viewers are expert coders, so I don't need to explain how this code is working, or the other codes I have already shared. Most of them are self-explanatory, and if someone doesn't understand, then he or she can contact me via email or via some other platform, or also they can contact me over the YouTube community by commenting on my video. So the code is pretty much this. It's just a RGB LED blinking. There is nothing special about it. And so far, if you have noticed, the coding, as I have stated in my last video, is not same as the coding we typically find with STM32s. And so there are a lot of differences. For example, in the case of STM32s, we have hell underscore GPI or something, and here it's GPI bit write and port, pin, and value. So it is similar but not same. And if you hover over any function, you will find the details about that function. And the Segger Embedded Studio gives you literally almost all the benefits of Eclipse IDE. So that's a real lifesaver. And then if you see the RCU, that is the clock peripheral. The clock peripheral is also not same as the clock peripheral you will see in STM32s or CH32s. GD32, in fact, in this segment, I will say that they haven't copied everything from STM32s. They might have studied STM32s a lot, but they didn't copy totally. They tried, I believe, to replicate as much as possible, but not all. And this gives you two things. First, the platform is not 100% bug free. There are some issues. Particularly, I have faced some issues with the UART hardware because the UART interrupt doesn't work. I have tried a lot of ways. In fact, I have also tried to resolve the issue by using ChatGPT and other AI platforms, but even their solution didn't work. So it's definitely a hardware issue. I don't know if someone from Giga Device is watching this video or not. If he or she is watching it, then I suggest that please tell me if I am wrong, or if it is really something to do with your hardware, because frankly speaking, I have tried a lot of ways, but it didn't work at all. And the second thing is, there are some minor issues, not that much serious, but there are some minor issues that sometimes gave me a feeling that either I have bricked my microcontroller, or there are some other coding issues that I have not seen. but in reality I found that the case is totally different. So you have to be careful about the issues, and of course there are other workouts or way arounds which can be used to resolve these things. For example, in my case, since I was not able to use the UART interrupt anyway, but I had to do the project, so I used DMA transfer rather than UART. So from case to case, things might get tricky for you, but you have to be careful if you are coding for something commercial. So I will suggest that you go by modular steps, or in other words I will say that you go step by step, not everything in one complete code. You test one hardware at a time and then you go for it. So in that way you can resolve your issues efficiently. So this is the basic code, and in terms of software, yes, there are some issues also that also need to be addressed before successfully coding the GD32VF103 series. Fortunately, I have made this video so that people will get help from this video and have their issues resolved. So without much more delay, I will show you the other things regarding GD32VF103 series. So these files are the peripheral files that you will be needing to work with the internal peripherals, and they vary from series to series, and as you can understand, every series or every microcontroller has its peripherals uh, in different numbers and with different features. Some may have two ADCs, some may not have two ADCs, some may have CAN hardware, some may not have CAN hardware. So from series to series, or from microcontroller to microcontroller, things may vary, so these files will also vary. So be sure of using which family you are using in your project. In my case it's GD32VF103 series, so all files related to GDVF103 series are included. But be aware, GD32VF103 has several other microcontrollers. Let me show you. The data sheet. So this is the GD32VF103. Then this series ends with other letters like RB, R8, R6, R4, etc., etc. And you can see there are differences with flash, RAM, timers, and other hardware. The same can be also applied to the other uh, microcontrollers that end with TB, T8, T6, etc., etc. serial. So these files are generic. Not all peripherals may not be available in your particular microcontroller. So this is handled by the compiler itself, so you don't need to worry, but you have to pay some attention whether you are working with the right stuff or not. And again, coming back to the same topic, you see that this GD32VF103 Cypet long gun board has alternative pins also. So this is another thing that we need to be careful with. As with any ARM microcontrollers, pin swapping or pin multiplexing is common. So a combination of hardware, datasheet, and the library functions is a must. Another thing I wanted to point out here is the fact that there are some issues with naming also. I mean, there are some spelling mistakes, there are some grammatical mistakes, but I don't think that's issue with coding. But to me, a spelling mistake is a very big thing. It gives a bad impression of your work. So this is one such example. In case of dual, it's daul, so it's obviously a wrong word. It should be dual, that is two. But functionally it's okay, functionally it will work. So these are the things that one should first think before using GD32s, and these are the things that will bother a lot if you don't know. So this is a ready-made code, but let's see how we can make a code on our own. So before making the code, a sample code on our own, let me tell you one more thing, and that is always be sure to include the source and the header files, and the process is different from other IDEs. So here I will show you how you will do this thing. So without the source and the header files, nothing will work and you will get a lot of error. As in this case, there is no error. If I build, there is no error, nothing. It's building. Okay, wait, let's wait for some time. And there are other options, as you will find with any IDE. There are options for search, there are options to view memory usage, local variables, registers, etc., etc., etc. If you have a Segger debugger, then if you are able to use it with your microcontroller, then you can have other options also. So now it's compiling. You see, this is the code is generated, and the flash memory is only 3.6 kilobyte. Of it has been used out of the 64 kilobyte, and the same goes for RAM. Only 2 kilobyte out of 20 kilobyte has been used in this full project. There are some 6 warnings. Let's see what these warnings are. There are some small notes, but the code will work. It will not have any issue at all. So let's move on. Close this solution. Open a new project, and the new project, in the new project you have to first select the GD VF103. So in my case, just write the VF103, no, not 103, VF1, and there are 4 options. The first one is a C++ executable, that is a firmware for GD32VF1 XX series microcontroller. The second one is assembly code. The third one is an externally built external executable code, that is also a firmware, and a library for the Giga device. So we'll select the first option because that's the thing we will be wanting. And the second thing is optional. You can select where you want to put your code. In my case, I want to put it in my working folder, GD32, this one. I can make a new folder like test code, test_code. Select this folder and give a name to your project. In my case, that will be a test code. It can be anything. Okay. So it says import all files and package files. Yes. Finish. So now the project is semi-ready, not fully ready. As you can see, the main is just a template. It's nothing. From here, from the option solution, we go to the option and we select two things: optimization, optimization level. Optimization level, it should be balanced. It's none at the moment. It should be balanced. Balanced means between speed and code size there is a compromise, but is the ideal thing to select. If the level is 0, then there is no optimization, fastest compilation, and best debugging experience. So these are the things. If you optimize more, the code size will be reduced, but there could be issues with speed, or there could be issues with reliability also. So I have opted for balanced. And I will also be needing bin files to additional output format. It should be binary, because that's the file format recognized by the programmer software, the GD32 all-in-one programmer. So this will be needed. So these are the two modifications I will be needing. So let me show you one more thing before moving on, what happens with and without optimization. So it has been set to balance, but previously it was none. So it was none, now it's also none, and we will be needing the source file. Now there is no source file. In my experience, I have found a lot of issues with the official firmware library that the GD32VF103 series has. This is the standard library, the source, and the header files are here. You can download it from the GD32MCO.com website, and after having faced all these issues I have mentioned in my past lecture, I have selected the optimum library functions that I will be needing. Optimum in the sense that I have made some modifications, like the dual word has been changed instead of daul, and I have made some minor modifications that otherwise would hamper my code compilation. So these are the things, and I have also included additional libraries like the ST7735 TFT display library, which is not available with the official device firmware standard library, because in my examples I have used that display a lot of times. So these are the modified device library files. So I will include stuffs from here. The including process is very simple. Just copy these two folders and go to your project location, in our case test code, then go to GD32VF106 folder, 1xs folder. You can go to devices and just delete these two folders and replace them with the ones I have copied. So now things are copied, and now I should include the necessary files or all the files. It's better to add all the files because only the ones that will be used will be included and the rest will be ignored. So add existing file because they are already existing in the project folder. So go to source, select all, then add. Now there is a warning, file already in project. It's asking what should it do. So it's asking should it duplicate or not. So our choice will be no, 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 all no. So now we can get rid of this template in the main C code and write code as per our requirement. So we start with hash include GD32 header file and also add hash include sysdig.h. Alright, now void main void and while one loop. So that's the basic structure of the coding. If we build, see it's getting built and there is no error. Now let's see what happens with the optimization enabled to level 2. Balanced. Okay. Now let's build the code. You see the code size is getting a little bit smaller. Last time it was 1.9 kilobyte and now it's 1.5 kilobyte. So a little bit of code has been optimized. By default, the GD32VF103 runs at 108 megahertz clock speed instead of 72 or some other clock speed that we will typically find with STM32s. So we must be looking carefully the header file for the sysdig to change for time delays if needed. Let me show you. So by default the external 25 megahertz clock has been coupled with the PLL, internal PLL, to generate the 108 megahertz clock speed. Another thing to note is if you can't find what you are looking for, you can always hit control and then hover over the function you want to find its location to. For example, in my case here, I wanted to find out the system core clock speed, that is the system core clock speed is set to 108 MHz using PLL and external 25 MHz crystal on board the Cypet-Longan board. So that's the speed. If you want to use some other speed, you just uncomment uncomment the speed you want to use, and it will be done. So you don't need to set the RCU manually. But yes, of course, setting the RCU manually will help you to optimize your clock requirements for low power applications and power optimization also. So this is about the clock. So now let's see what happens if I write GPIO. Then you can see there are some suggestions popping up. So let's initiate one pin GPIO IO90. So after having it clicked, this function is partially completed and popped out. So the first thing we will be needing, which peripheral we will be using. For example, if I write GPIO port C, then this is the peripheral I have selected for the GPIO peripheral. And the next thing will be mode and speed. The mode and speed, I think everybody knows what mode and speed are in STM32s and CH32s as well. This is common for these microcontrollers. So mode is GPIO underscore mode. If I write mode, then there are options for push pull, alternative function, floating, input pull up, input pull down, etc., etc. So let's say mode output push pull. Control and space bar, mode push pull. Now let's select the speed. So GPIO underscore speed. Oh, not speed. GPIO underscore speed. Let's say 50 megahertz, and the pin GPIO underscore pin. Let's say pin 13. That is the red LED pin. So now we have initiated the red LED pin as per this pin map. So the red LED is connected to PC13, and we have initiated this pin to be an output so that we can toggle this LED. So the next thing we'll be needing to toggle this. So GPIO state should be changed. GPIO white. GPIO. Let's see what functions we have. GPIO output, bit get, bit set, bit write. So we can set bit, and it is just GPIO C peripheral and GPIO pin 13. We add some delay 1 millisecond times, let's say 1000. So it will set for 1 second, and then we wish to have it reset. and it will work. But there is one critical thing I forgot to do, and without that this code will not work, the LED will not blink at all, and that is I have to enable the GPIOC peripheral clock. So RCU peripheral clock enable, and the peripheral should be RCU underscore GPIO underscore GPIO C. So now the code will work. So if I now build it, so it's now built, the code size has been increased a bit. So now the code is ready for flashing. So let's go to the project folder. This is the project folder. Now we have another folder called output, and the output contains another folder called debug executable, and then the bin file. This is the bin file that we will be loading. So if we start the GD32 all-in-one programmer, at present there is no device connected, and that's because the GD32 board, the Cypher Longan board, is not in DFU mode, although it's connected to my PC, but it's not ready in DFU mode. So to do that, first I have to hold these two buttons. This one is reset and this one is boot 0. So after holding it, I will release the reset button and keep holding the boot 0 button until a new device pops up here. So I'm doing it here. See, now there is a GD DFU device 1, and the part number is GD32VF103CBT6. So now we can browse to our it's ready but not connected, so I'm connecting it. So now we can also erase, we can upload other stuffs, you can edit option bytes, but these are not needed. I have never used them, so I will keep everything as it is now. So let's browse to our project location, debug executable test code bin. So now it's ready. If I press the download button, it's already uploaded. It's just like the blink of an eye. It's so fast. So we can also verify after download, or we can just jump to the application after we have completed download, and this is the option I have usually used. Erase is not needed. Full erase in fact is not needed usually. Only necessary erase is my choice. So I keep all these things as they are. There is no need to erase the whole chip unnecessarily. This will affect the flash life. So this will be all for this video. I hope you enjoyed, and a like, subscribe and a share will be appreciated. Hope to see you in next video tutorial series on another family of microcontrollers. Till then, see you, goodbye, have a nice day, thanks.